This topic is about building a planning-grade workflow for ecological risk mapping with AI. The goal is not to do AI for its own sake. The goal is to produce risk information that can actually inform decisions, where to intervene, what to prioritize, and what uncertainties remain. Ecological risk mapping sits at the intersection of environment, infrastructure, and society. Hazards can include flooding, wildfire, heat stress, drought impacts, erosion, and ecosystem degradation. AI becomes useful when it helps scale analysis across large areas, fuse multiple data sources, or discover patterns that conventional manual analysis would miss. Throughout the presentation, the same quality rule applies. Every model output must be interpretable enough to support planning action. If you cannot explain the assumptions, training data, and limits, then you cannot ethically use the output in public-facing planning decisions. The session follows a workflow structure. We begin with learning objectives and the distinction between reactive response and proactive adaptation. Then we define ecological intelligence as a planning capability, sensing signals, mapping them, and turning them into decisions. Next, we cover big Earth data sources and cloud processing, Google Earth Engine, then contrast that with custom AI modeling in Python. We introduce digital twins and clarify how they differ from static risk maps. Finally, we move through the core pipeline, pre-processing, model training, validation, and explainable AI, then discuss real-world adoption issues and end with a mini-project that links directly to next case study topic, Atlas to stress test to action. By the end of this topic, you should be able to describe an end-to-end AI risk mapping workflow suitable for planning use. That includes selecting a hazard definition, collecting and documenting data sources, pre-processing, choosing a model type, validating results, and interpreting outputs as decision support. A second objective is tool literacy. You should know when cloud platforms like Google Earth Engine are the right choice and when a custom pipeline is justified. A third objective is critical. Understand why model accuracy is not the only evaluation criterion. Interpretability, bias, uncertainty communication, and governance context are part of planning grade quality. Finally, you should be able to connect your workflow to broader adaptation practice, how risk maps feed stress tests, dialogues, and planning instruments. In other words, AI is one piece of a larger decision system, not the whole system. Reactive resilience is what happens after damage, emergency response, repairs, and recovery. Proactive resilience is what happens before, risk reduction, adaptation, and prevention. The same city can be good at reacting and still be strategically fragile if it keeps rebuilding the same vulnerabilities. AI and remote sensing matter more on the proactive side. They allow early detection, monitoring, and predictive screening. They help identify where hazards are likely to occur, where exposure is growing, and where interventions will have the highest benefit. But proactive mapping has a trap. It can create false certainty. A map can look authoritative even when it is built from weak assumptions or biased training data. So, the planning task is to pair predictive capability with epistemic humility, be explicit about uncertainty, and treat maps as decision aids rather than verdicts. A practical rule: if a model output would change where money is spent or who is regulated, the QA burden must increase. Planning is not a sandbox, it is governance. Ecological intelligence, in this context, is the capacity to understand environmental signals and translate them into spatial decisions. It combines three elements: knowledge, what hazards and processes matter; skill, how to map and analyze them; and judgment, how to act under uncertainty and ethical constraints. AI can enhance ecological intelligence by fusing many predictors, learning complex relationships, and scaling analysis. But AI can also damage ecological intelligence if it replaces understanding with automated outputs that no one can explain. A planning professional should treat AI as a partner, not a replacement. Use it to extend your ability to see patterns, but maintain responsibility for interpretation. That means setting the hazard definition clearly, selecting predictors based on domain reasoning, and ensuring outputs are communicable to non-technical stakeholders. This is also where the module's learning outcomes show up: technical competence, critical evaluation, and the ability to advocate for resilient solutions using evidence rather than slogans. Most ecological risk mapping workflows start with data. Big Earth data includes satellite imagery, derived products, like land cover or vegetation indices, climate reanalysis, terrain models, hydrology layers, and socio-economic exposure layers. A typical remote sensing stack might include optical imagery for land cover and vegetation, radar for moisture and flooding sensitivity, and digital elevation models for drainage patterns and slope. Climate and weather data add the forcing conditions, rainfall intensity, heatwave frequency, drought metrics. For planning, data documentation matters as much as the data itself. You need to record source, date range, resolution, processing level, and known limitations. If you cannot defend the provenance, you cannot defend the model. Also remember, more data is not automatically better. A smaller set of well-justified predictors can outperform a large set of noisy predictors, especially when training samples are limited. Google Earth Engine is a cloud platform for large-scale geospatial processing without downloading massive archives. It is ideal for rapid screening, repeatable indicators, and prototyping national or regional analyses. The main advantage is computation plus ready data, satellite archives, terrain models, and many products are available. Typical planning uses include vegetation indices, surface temperature proxies, and historical water occurrence indicators. However, G is not a magic button. Dataset choice, masking, temporal representativeness, and validation still matter. Use G when you need speed and scale and when the workflow can remain transparent. Use Python when you need specialized modeling, deeper uncertainty analysis, or custom local data integration. A custom AI pipeline in Python gives you flexibility. You can choose specific algorithms, integrate local datasets, control pre-processing steps, and apply advanced validation strategies. This is often the right choice when the planning question is local, high stakes, or requires integration of proprietary or field data. In Python workflows, the responsibility increases. You must manage data splits properly, avoid leakage, document feature engineering, and control for overfitting. You must also maintain reproducibility, code versioning, parameter tracking, and clear documentation. From a planning perspective, the biggest advantage is interpretability control. You can choose models that are explainable by design, or apply explainable AI methods to complex models. You can also build uncertainty estimates and communicate them explicitly. The key is to avoid tool worship. Choose the platform that supports planning quality, not the one that looks most sophisticated. If you cannot maintain the pipeline or explain it to stakeholders, it becomes a liability, not an asset. Digital twins extend the idea of mapping into simulation. Instead of static layers, a twin attempts to represent a system dynamically, often integrating sensor feeds, operational models, and scenario simulation. In urban contexts, twins can simulate heat distribution, air quality, flood routing, and infrastructure performance. Digital twins can support what-if questions. What happens if we add green roofs, expand retention basins, or change traffic patterns? This is attractive for planning because it links interventions to outcomes. But digital twins also raise issues: cost, opacity, and the risk of vendor lock-in. A twin is only as good as its data streams and calibration, and it can create false confidence if its uncertainty is not communicated. So, treat digital twins as one end of a spectrum. For many ecological risk mapping tasks, a transparent indicator-based workflow plus periodic stress testing can be more feasible and more auditable than a full twin. Choose the level of complexity that matches the decision needs. Pre-processing is where many AI projects succeed or fail. Raw pixels are not comparable across time and space without correction. Handle clouds, sensor differences, and temporal aggregation. For ecological risk mapping, pre-processing also includes feature engineering, NDVI for vegetation health, surface temperature proxies, topographic wetness indices, distance to water, or impervious surface fractions. Each feature should have a clear rationale. A planning-grade workflow documents these steps so others can reproduce them. This matters because decisions must be defensible. Also, pre-processing is where you can reduce bias, improve sampling, align features to seasonal hazards, and remove spurious predictors. Model choice depends on the task and the data. For classification problems, e.g., susceptible versus not, tree-based methods like random forests or gradient boosting often perform well and can be relatively interpretable. For complex spatial patterns or image-based tasks, deep learning can be effective but is harder to explain and validate. Planning workflows should treat algorithms as tools, not identities. Choose the simplest model that meets performance needs and supports interpretation. If a simpler model is nearly as accurate as a complex one, prefer the simpler one for governance reasons. During training, the biggest technical risks are overfitting and leakage. Overfitting means the model memorizes patterns in the training data that do not generalize. Leakage means you accidentally allow information from the test set to influence training, leading to inflated performance. Use robust evaluation design, spatial cross-validation when data is spatially clustered, temporal validation if conditions change over time, and careful feature selection. A model that looks perfect on paper but fails on new areas is worse than a modest model that generalizes reliably. Validation is not optional. It is the boundary between science and storytelling. For classification, common metrics include accuracy, precision, recall, F1 score, and AUC. But the choice of metric must match the planning objective. If the goal is early warning or screening, recall may matter more. You do not want to miss high-risk areas. If the goal is targeted investment, precision matters. False positives waste limited resources. Often you need a balanced view. Validation also needs to consider spatial structure. If you randomly split pixels, you may overestimate performance because nearby pixels are similar. Spatial cross-validation helps test whether the model generalizes to new neighborhoods. For planning, the most important validation outcome is credibility. You must report metrics, explain the validation design, and state limitations. And you should provide uncertainty, confidence intervals, ensemble spread, or at least qualitative uncertainty categories. A map without validation is not evidence, it is decoration. Explainable AI, XAI, is about making model behavior understandable to humans. In planning, XAI is not a luxury, it is part of accountability. If a model influences zoning, infrastructure spending, or risk communication, stakeholders deserve an explanation. Some models are interpretable by design, like decision trees or linear models. For more complex models, post hoc methods like feature importance, partial dependence, or local explanation methods can be used. The goal is to answer questions like, which factors drive high susceptibility, and are those drivers plausible? XAI also supports error diagnosis. If a model predicts high risk because of a spurious correlation, you can detect and correct it. If it depends heavily on one noisy feature, you can redesign the pipeline. But XAI has limits. Explanations can be misleading if they are not validated, and they can create a false sense of understanding. So, treat explanations as evidence to be tested, not as final truth. The standard is, explain, check plausibility, and document uncertainty. This case example illustrates that risk mapping is inseparable from context. In many Global South contexts, exposure and vulnerability patterns differ. Informal settlements, limited drainage capacity, and uneven service access can make hazards more damaging. AI can help by mapping susceptibility at scale, but it can also amplify inequity if training data is biased or if outputs are used to justify exclusion. For example, a high flood risk map could be used to deny services rather than to invest in resilience. So, the planning move is to pair risk maps with a justice lens. Ask, who bears the risk, who benefits from interventions, and how will results be communicated? Also ensure that validation data reflects local realities. Models trained in one region often fail in another. This is a reminder that ecological risk mapping is not just a technical exercise. It is a governance act. The same output can support adaptation or enable harm, depending on how it is embedded into policy and decision processes. Urban air is a useful example of a digital twin approach focused on urban heat and air quality. The value proposition is high resolution, near real-time information that can support operational decisions and longer-term planning. For ecological risk mapping, this shows what hyperlocal means: street-level variation, microclimate effects, and behavioral responses. These details matter for heat risk and exposure because the difference between shade and no shade can be the difference between safe and dangerous conditions. At the same time, a twin model requires data streams, calibration, and long-term maintenance. This raises governance questions: who pays, who controls the model, and who can audit it? If the twin becomes proprietary, transparency can decline. The planning lesson is to treat digital twins as one tool among many. They are most useful when they answer a decision question that simpler maps cannot. Otherwise, they risk becoming expensive showcases with limited policy impact. AI is not only for hazard mapping. It can also support restoration planning by identifying degraded areas, selecting intervention types, and monitoring outcomes. The key is to treat ecosystems as dynamic systems with feedback, not as static land cover categories. In restoration contexts, AI can assist with prioritization: where will investment produce the highest ecological benefit? It can support monitoring by detecting changes in vegetation condition, soil moisture proxies, or land use pressure. However, restoration planning also shows the limits of purely data-driven methods. Local ecology, governance constraints, and community needs often determine success more than remote sensing indicators. So, AI should be used to inform decisions, not to automate them. A planning-grade restoration workflow includes stakeholder input, explicit objectives, and evaluation criteria. AI contributes evidence, but the final choices must reflect values, trade-offs, and feasibility. This connects back to the module's governance learning outcomes. Planning decisions are social choices supported by technical evidence. Implementation pathways matter. Sprint is an example of translating research methods into usable prototypes and services. The pattern is common. Universities and companies collaborate, then refine outputs until they fit real user workflows. For planning agencies, adoption depends on trust and capacity. Staff need training, tools need support, and outputs must align with decision cycles. Otherwise, AI products remain nice reports that do not change action. When you evaluate any AI workflow, include implementation readiness. Can it be repeated, updated, audited, explained to stakeholders? Those questions often matter more than squeezing out the last few points of accuracy. The smart city framing can be seductive because it promises technological solutions to complex problems. But ecological risk is not solved by dashboards. It is reduced by governance, investment, and behavior change. Key risks include opacity, models no one can explain, data injustice, communities observed but not served, and techno-solutionism, ignoring social and political drivers. There is also the risk of displacement. Risk maps can be used to justify exclusion rather than resilience investment. A critical stance does not reject technology. It demands accountability. That means clear problem definition, validation, transparency, participatory interpretation, and safeguards against harmful use. For planning professionals, the ethical standard is simple. If your model output could harm people, you must build processes that prevent misuse. That includes careful communication, stakeholder involvement, and the ability for affected groups to challenge and contest the mapping results. This slide turns the topic into a concrete task. The mini project asks you to build a small but complete ecological risk map workflow, either in Google Earth Engine or in Python. Choose one hazard, flood, wildfire, or heat, document your data sources, and run a model or indicator pipeline. You must justify model choice and report a validation metric. But you must also interpret results for planning. That means explaining what decisions the map can support and what decisions it cannot support. The connections matter. Next topic shows the downstream governance workflow. National layers and local stress tests lead into risk dialogues and planning instruments. Your mini project should anticipate that downstream use. Treat this as training for professional practice. The output should be reproducible, explainable, and honest about limitations. If your workflow cannot be explained to a municipal planning team, it is not yet planning grade. The core message of this topic is that AI is a method inside a broader planning evidence system. A good ecological risk mapping workflow starts with clear problem definition, uses appropriate Earth observation and contextual data, applies a model that matches the task, validates performance, and communicates results responsibly. Tool choice, G versus Python versus digital twins, is not a status competition. It is a fit-for-purpose decision shaped by scale, capacity, transparency needs, and governance context. Quality is multidimensional: accuracy, generalization, interpretability, uncertainty, bias, and implementation readiness. If you improve accuracy while losing transparency and fairness, you may reduce decision quality overall. Finally, remember that risk maps are not the end. They become inputs to planning cycles, stress tests, dialogues, prioritization, and implementation. If your workflow cannot connect to those steps, improve it until it can. That is how AI becomes useful rather than ornamental.